Hey there, 205. This is going to be a little bit of a longer video, but it's important that it's all in one place. So do your best to listen up. We'll do one fun thing at the end. So we are moving into a unit on linear regression. We also call this ordinary least squares regression, and you'll have a homework assignment related to it. So it's important that you understand. So we have talked about what data looks like once you collect it and how to run correlations between two variables. We said a correlation can show us something about the strength of a relationship and the direction. Today we're going to talk about linear regression and how it works behind the scenes, and then in future videos we'll talk about what it looks like when you do it on a computer and how to interpret it from the computer output. So last time we talked about this thing called correlation, but we can do more than correlation. Correlation is the most basic thing that you can do to look at relationships between variables. We can quantify how much y, our dependent variable, changes if x changes by using this thing called a linear regression. Okay, the regression is going to tell us three things. It's going to tell us the strength of the relationship, the direction of the relationship, and something called the significance of the relationship. We'll get to that in future videos. But let's walk through this. So to run a linear regression, there has to be a few requirements that are met with your data. So first of all, your dependent variable must be continuous, which means in our class, it has 7 levels or amounts at least. So a percentage that ranges from 0 to 100, that's continuous. A scale that goes above 7 points, that's continuous. There's lots of continuous stuff. But this is where you actually have to know what continuous means. If you try to do a linear regression with a dummy variable that just has a 0 or a 1 for your dependent variable, this will not work. So actually knowing those classifications really matters. And also the relationship between the variables, you need to at least think that it's a linear relationship. So as one goes up, the other goes up, or as one goes up, the other goes down, something like that. So those are the requirements. So let's talk about how a regression actually works. Here's what's going to happen. You have a data file. We talked about that last time. It looks like a spreadsheet. The computer is going to take your data and it's going to plot it. Here on the right-hand side, we have a fake plot with an x-axis and a y-axis. It's going to plot your data and it's going to draw what we call a best fit line through the data, okay? A best fit line, you've heard that before. A best fit line means that it's minimizing the amount of space between the line and the data points on average. It doesn't have to hit every data point. In fact, it never really does, but it's minimizing the amount of space between all of the data points and the line. Now that line has an equation that comes with it, and that equation looks like this. Y equals A plus BX plus E. This should look a little bit familiar to you because it's the same as something you probably learned in middle school when you learned Y equals MX plus B. That's the same thing. We just do it a little bit differently at this level and we add on this one letter. So that line, and we're going to walk through what all of those things mean in that equation. That line and that equation represent the relationship between your independent variable x and your dependent variable y. So let's walk through each piece of this equation so you know what everything symbolizes. So the y is actually something that you guys already know. Those are the values of your dependent variable. So you have that spreadsheet, you have your dependent variable that has different values for every single unit. That's what y means. The a term represents what we call the y-intercept, or the constant. If you did y equals mx plus b in middle school, you probably know what a y-intercept is. It's where that line crosses the y-axis. So when a line crosses the y-axis, that is the expected level of y when your x variable equals 0. This is the baseline amount before we take x into account. I'm going to show you guys an example of this in just a few minutes that will bring a lot of clarity to it if you're confused already. But that A symbolizes where the line crosses that y-axis. The B in this equation up here is the slope, or what we call the regression coefficient for your independent variable, which is x. Again, you know what x means in this equation because we've been talking about x this entire semester. So this is the slope, or what you guys learned as the rise over the run when you were in middle school. So this is how much does the dependent variable go up or down if the x variable goes up by 1 unit. So we've been saying for many months, as x goes up, y goes up. As x goes up, y goes down. This B actually is going to tell us how much y actually goes up when x goes up by 1, or how much y goes down when x actually goes up by 1. So that's what B stands for. It's the slope. E, which is a little bit of an oddball in the equation, is called the error term. I'll explain this a lot more in detail later, but this is the portion of the dependent variable that cannot be explained by A or by B. Okay, so I think an example will be very instructive here. Here's our example. Let's pretend that we are interested in what affects how long a jail sentence is, right? Some people spend a long time in jail or prison. Some people spend a short time. We're interested in what variables predict someone's prison sentence length. There's many variables that could predict this. It could have to do with your number of prior convictions. It could have to do with the age of the judge, the nature of the crime, the race of the defendant. But let's pretend that we're interested in our independent variable being someone's number of prior convictions. So over here on the right, we have a fake data set. So here up on top, this person in our sample has 0 prior convictions and they spend 12 months in jail. This person has 3 prior convictions and they spend 13 months in jail, and so on and so forth. That's the data in our data sheet. Okay, so we have our independent variable, our number of prior convictions, and our dependent variable, how long people spend in prison measured in months. What is the computer going to do with that data? It's going to make a scatter plot. So here's the same data on the left. And if we go over to the right, okay, so our person up here had 0 prior convictions. Okay, they have 0 prior convictions, but they spend 12 months in jail, so that dot represents them. And it does that for every person in the sample until we get a scatter plot. Okay, next step. Then it's going to draw the best fit line through that scatter plot. So this is a line that minimizes the distance from the data to the line. And that line comes with our equation, y equals a plus bx plus e. We're going to make the e invisible over here. But once we draw that line, these are the numbers that are associated with that line. The little hat on top of the y just means this is the equation for the line rather than the data itself. So this is what we're working with. Now let's go through the interpretation of this 14 plus 3x. So what do A and B mean in this example? Well, we know that A is the constant, or the y-intercept, It's the value of y when x is 0. So go down here. When x is 0, all the way down here, y equals 14. That's where that 14 came from. It's where the line crosses the y-axis. So that's our y-intercept, or what we call our constant. That's where the 14 comes from. So what this means in plain English is, on average, people who are getting convicted will serve a 14-month sentence when they have 0 prior convictions. Because remember, this line is like averaging everything out. So on average, someone that has 0 prior convictions will serve 14 months in prison. So what does B mean? Well, in our example, B equals 3. Up here it says 3x. X just stands for prior convictions. Okay, so what does that mean in plain English? A 1-unit increase in prior convictions leads to a 3-month increase in prison sentence. Remember that we said you interpret this by doing, when x goes up by 1, how does y change? So in our example, if the number is 3, when prior convictions go up by 1, so on average, when someone has 1 more prior conviction, on average, they're going to get 3 more months in prison. That's how you would interpret that. If the coefficient was negative, so if that number up here said -3, we would say a unit increase in prior convictions, so 1 more prior conviction on average, leads to 3 months less of a prison sentence, which doesn't really make sense. But if it came out negative, which the numbers often do, that is how you would interpret it. So what is the deal with the E term in the y equals a plus bx plus e equation? Let's talk about that. As you could see, our line does not perfectly predict each value of y, right? Many of the data points are deviating from that line. So there's a lot of space between the data point and the line here. There's a little space between the data point and the line here. We call these deviations errors, or sometimes residuals. Think of the word of residual as the leftovers. This is the difference between our observed values, i.e. our real data points, and our predicted values. When we say predicted values, we mean the values of the line. So there's a difference between the real data point and where the line is. You can just do a simple subtraction to get that number. So if y over here is 48 coming from our y-axis, and y hat, which is what we call the line, is 38 over here, there's a difference of 10. So these are the residuals, or the leftovers. What do we do with them? Our computer will use that little subtraction, or that difference, to calculate a statistic called an R-squared value. And I'm going to have you guys interpret this in your homeworks. So an R-squared value, this is where people get a little confused. An R-squared value is a number that's going to range from 0 to 1. It's a proportion. It's going to tell us the proportion of the variance in our dependent variable y that is explained by x. Because remember, we're trying to explain why some people have a lot of time in jail, some people have a little bit of time in jail, and some people have not a lot of time in jail at all. There's a lot of variance on that variable. It can go up and down. So this is telling us how much do prior convictions explain that variance. So for example, if the R-squared value came out as 0.23, that means that our independent variable is explaining about 23% of that variation in people's time that they spend in jail. So in our example, prior convictions explain 23% of why people in our sample get the prison sentence length that they do, okay? An R-squared is also known as a fit statistic. How well does the model or that line fit the data, those dots? So the tighter that the dots are to the line means that they're following the observed relationship. That's going to give you a really high R-squared. So down here is a picture of an example. If our dots were all really, really close to the line, they are fitting the line really, really well, that means that our independent variable, prior convictions, is really, really explaining why people get the prison sentence length that they do. That R-squared is going to be really high. If the dots are really, really far away from the line, their X variable is not predicting the Y variable very well, and that R-squared value is going to be closer to 0. So this is what we mean by a fit statistic. How well does the independent variable or variables explain our dependent variable? So that's what a regression is doing behind the scenes. It's taking all of this data, it's plotting it, it's popping out numbers that correspond to pieces of this graphic, and then you can use those numbers to interpret the relationship. For every prior conviction people get, on average, their prison sentence length goes up by 3 months. That's how we would do that.